Well, good afternoon, everybody. So the topic of today's lecture are the bitwise operations that you can perform in C. And so these operations are probably unusual for most of you. I don't think most of you have seen these operations before. I would say most programmers in the past 20, 30, 40 years maybe, probably weren't taught these things in school. So these were the things that you would learn many, many, many years ago in computing science. But they're not often taught anymore. So the bitwise operations are concerned with performing operations at the bit level, right? So being able to flip a 1 or a 0 to a 0 or a 1, or doing other operations with individual bits. Most programmers don't have to deal with this sort of stuff in today's world. So the ones who do would be people who, for example, write compilers, of which there aren't very many of those. And for people who are really concerned with very, very high performance operations. So your general CPU in today's world does not actually let you go in and touch an individual bit, right? So you know that that data on your computer is zeros and ones, right? There's no way for you to go in and say I want to change that 0 or I want to change that 1. The best that you can do is grab a bunch of bits and then, with some other operations, go in and fiddle with an individual bit in that group of bits. But you can't index or address any individual bit on a modern computer. But you can perform operations on groups of bits. And these operations tend to be very fast. So if you know what a CPU cycle is, most of these operations can happen in a single CPU cycle. And so this lets you do some very, very clever things very quickly. But the applications are generally, most programmers generally aren't interested in this sort of thing. If you are interested in this sort of thing for whatever reason, this is one of the resources that you can look up. So it's a book called Hacker's Delight. It's resource number 2 in this list here. It's basically 480 pages of algorithms that deal with playing around with bits. And there's a lot of information in here, most of which is not really applicable for most programmers. But if you're one of these rare programmers that has to deal with this sort of thing, this is an invaluable resource. The other types of programmers who do have to deal with this thing routinely are the ones who do embedded programming. So the people who program devices where there's very little, or compared to a modern computer anyway, very little memory or very few other resources, often have to resort to bit-level tricks to implement the programs that they want to implement. So throughout this notebook, I'm going to be using this function here. This function simply takes an integer value and prints it out using zeros and ones. So it prints it binary representation. The input to the function is, we haven't seen this before. So this type here is uint 8_t. So the C standard does define integer types that have a specified width. They're not guaranteed to exist on your computer or in your compiler. So it's compiler and computer dependent. On any desktop computer, these things exist. So in the header file, standard int.h, you can find a bunch of different types that are declared for you. Right? So int 8_t is an signed int value consisting of exactly 8 bits. Right? Int 16_t is a signed int value consisting of exactly 16 bits, and so on and so on and so forth. Right? This is you want to contrast this to just a plain old int in C, and you don't know how many bits. You don't necessarily know how many bits make up an int on your particular computer. Right? So if you do need integer values of a specified width, they do exist, but you have to include this header file, and your computing system and compiler have to support them. So I know on my computer, uint 8_t is supported, right? So it's an 8-bit unsigned integer value. And so this function here simply prints out the bits of the number from most significant bit to least significant bit. You probably won't be able to understand the function's implementation right now, but by the end of this notebook, hopefully you'll have an idea what's going on. All right, so the first operation we want to look at is bitwise not. Okay, so a bit is either 0 or 1. The not operation applied to a bit simply flips it to the other bit, right? So 1 becomes 0 and 0 becomes 1. Right? So if x is the bit 0, then not x is the bit 1. If x is the bit 1, not x is the bit 0. Again, in C, you can't actually toggle an individual bit, but you can toggle a group of bits. So the tilde operator is the bitwise not operator. If you apply it to an integer value x, like that, right, that gives you the not of x, right? So flips all the bits and gives you the corresponding value. It doesn't flip the values of x, flip the bits of x. It computes a new value where the new values bits are the flipped versions of the bits of x, right? But it doesn't change x itself. Right. So bits in x that are 0 become 1 in y, and bits that are 1 in 0 in x, sorry, become 0 in y. Right. So if x is that sequence of bits there, then tilde x or not x is that sequence of bits there. If you know what the 1's complement is, taking the not of an integer value is equivalent to taking its 1's complement. If you don't know what it is, it doesn't matter. So here's a little program. It uses that function I showed you earlier. Right? It takes the number that I showed you in the example. So that turns out to be 18. Right? In GCC, you can write binary numbers like that. So 0b, and then the sequence of bits that you would like in your binary number. So you could also write 0b, 001, 0010 if you like. On the next line, I compute the not, right? And then I print it out. And so you can see that x has that value there. If you flip the bits, you get that value there. All right, so in the previous lecture, we saw that modern CPUs use 2's complement. Right? And in 2's complement, if you compute the negative of a value, that's the same as taking the 1's complement and then adding 1. Right? Flip the bits, add 1. And so you can show that in a little program here. Right? So here I've got the value 99. Right? If I want to compute negative x, right? Obviously you would just write negative x. If you wanted to do it the hard way, right, you can take the not of x, right, and then add 1. Right? This is probably the way it's done on your CPU. So internally, this is probably what happens. Right? Print out the values, and you get 99 and minus 99. Right? And this works regardless of what the value of x is, right? Except for if x happens to be int min. Right? So int min is the smallest or most negative integer value that can be stored in an int. Right? So if you plug in int min here, whoops, int min, and run that, right? Well, there's int min, right? So roughly minus 2 billion. If you negate that, you get minus roughly 2 billion, right? And so that was also what we saw in the previous lecture, right? There's one integer value for which taking its negative or multiplying it by -1 or dividing by -1 doesn't work. And that's simply a consequence of the fact that the integer types occupy a fixed amount of memory, right? And we're using 2's complement to represent the number. Okay, so that's not. Not surprisingly, there's an and an or. Right? So bitwise and, if you just imagine 0 is false and 1 is true, this is the exact same thing as you can figure out what the values are when you compute the and. Right? So 0 and 0 is 0, right? False and false is false. Right? 1 and 0 is 0, 0 and 1 is 0. Right? Only if both x and y are 1 is the and equal to 1. Right? So some of you probably at some point in the past, either in Java or in maybe in this course, instead of writing the double ampersand for your logical and, you probably wrote the single ampersand. So the single ampersand, so it turns out in C it works. It's less efficient, but it works. And what you're actually doing is you're taking the bitwise and of your two numbers. Right? And so the bitwise and simply goes bit by bit in the two values and computes the and of the corresponding bits. So if x is that number there, or is made up of those bits there, right, and y is made up of those bits there, then the and of those values, you just go bit by bit. So 0 and 0 is 0. Right? 1 and 1 is 1, right? 0 and 1 is 0, and so on and so on and so forth. Right? So the value of x and y is whatever that value happens to be there. Right? And again, the demonstration program simply replicates this example up here, right? But it doesn't encode so that you can actually see the result. So if you run that, right, if there's your value of x and there's your value of y, take the bitwise and you get that. So bitwise and turns out to be one of the main building blocks of a lot of these algorithms described in this book. The following relation is true for bitwise and. So if you have some bit x, the value of x and 0 is always 0. Right? It doesn't matter if x is 1, anything and 0 is 0. Right? Similarly, the value of x and 1 turns out to be the value x. Right? So if 0 and 1 is 0, and 1 and 1 is 1. And so using these relations here, you can compute or you can form what's called a mask. So a mask is just a number, right, made up of some bits. So here I've got the mask equal to 1, right? That's the decimal value 1. Right? If I compute the bitwise and of the mask with x, right, what does it do? Right? Well, everywhere in the mask where the bit is 0, right, when you compute the and with x, you're also going to get a 0. Right? So you can imagine that the mask is unselecting all of these bits here. Right? We don't care what those values are. Right? Where the mask is 1, it's going to tell you the corresponding value in x. Right? So here, when you take the and of x in the mask, right, you get the value of the least significant bit in x. Right? So if x is even, the result is 0. Right? And if x is odd, there has to be a 1 here for x to be odd. Right? When you take the and of x in the mask, right, you end up with the value 1. So this turns out to provide an efficient way to determine if an integer value is even or odd. Right? It turns out to be more efficient than writing your if statement. Right? So is something odd? Right? Just take x, compute the bitwise and with 1, right, and check is the value equal to 1. And that will tell you if the number is odd. If you want to tell if it's even, just take the bitwise and with 1, and then check if the value is 0. And so the main function here simply calls is odd with some values. Right? So is minus 2 even? Yes, it is. I guess is it odd? So no, it's not. It's even. Right? Is minus 1 even or odd? Well, it's odd. Right? What about 0? 0 is going to be even. Right? 99 is going to be odd. Right? And so that's that is an efficient way to compute whether or not an integer value is even or odd. So this idea of using a mask is going to show up over and over and over again. So the mask doesn't have to be applied with and. You can use whatever bitwise operator you like to apply the mask. Right? Depending on the operator that you choose, you end up getting different results after you apply the mask. So using and lets you select any bit that happens whose value lets you select the bits in the mask. It lets you select the bits in x where the mask is 1. Right. So here I'm trying to select the least significant bit of the number. Okay, so there's an and, there's a not, there's also an or. Right? So or behaves the same as logical or. Right? So for 2 bits x and y, right, 0 or 0 is 0. Right? One of the bits has to be 1. At least one of the bits has to be 1 for the or to be 1. Right? So 1 or 0, 0 or 1, and 1 or 1 is equal to 1. Right? And so just like the single ampersand is the bitwise and, the single vertical bar is bitwise or. Right? So if you have x and you have y and you write x vertical bar y, right? You go bit by bit computing the or of the corresponding bits. Right? So 0 or 0 is 0. Right? 1 or 1 is 1. Right? So anywhere there's a 1 in this number or this number, you'll get a 1 in the result. Right? And again, the example here simply replicates the example. The code here simply replicates the example that's up here. Right? So if you run that, you see the result right there. So similar to the relation for and, there's also a relation for or. Right? So for any bit x, x or 0 is always equal to x. Right? So if x is 0, 0 or 0 is 0. Right? If x is 1, 1 or 0 is 1. Right? Similarly, x or 1 is always equal to 1. Right? And so using a mask, right, you can ensure that a subset of bits from an integer value x are equal to 1 while leaving the remaining bits unchanged using a bitwise OR. Right? So for example, there's my value x. Right? There's my mask, 0, 0, 0, 0, 1, right? Everything but 1. Right? So I can make sure, I can set the least significant bit of x to 1. So I can guarantee that this bit will be 1 no matter what the value of x is. Furthermore, all of the other remaining bits of x will be repeated in the result. Right? So those bits there are just those bits of x. Right? And I can guarantee that to be a 1 if I make sure there's a 1 in my mask and I use bitwise OR. Right? So if the least significant bit is already a 1, which it is here, and I apply the mask, right, it doesn't change that bit here. Right? And similarly, these bits here are just the original bits from x. Right? So the bitwise OR lets you guarantee that a bit in your result is a 1. So here I'm setting the least significant bit, but you can pick whatever bit you want to set. Right? So for example, I can set the bit corresponding to 2 to the 5, right, or 2 to the 5th power. Right? So 2 to the 5 is 32. So if I write x vertical bar 32, that sets the bit. So that's going to be 0 or 1. That's 2, 4, 6, 8. Sorry. 2, 4, 8, 16, 32. So it's going to set that bit to a 1. Right? You guarantee that bit gets set to a 1 every time. And this turns out to lead to a very stupid trick. So if you're using ASCII, you can convert uppercase letters to lowercase letters by writing that, which is sort of surprising. So let's take a look at what's happened. Okay, so here's my alphabet as a string. Right? I've got a little loop that's going to loop over the characters of the string. Right? Now I'm going to go into the string and grab an individual character, and that's going to be in uppercase. Right? I'm going to compute the OR of the letter with 32, right? And then I'm going to print out the result as a character. Right? And when you run this, right, it converts everything to lowercase. Right? And why does it do this? It turns out that the difference between the uppercase letters and the lowercase and the corresponding lowercase letter happens to be a difference of 32. So when you look at the encoding of the English letters in ASCII, right, they differ by 32. And so by playing this trick here, you can convert from uppercase to lowercase. So not the most useful thing to do in the world, but it shows you one of the things that you can do. Bitwise exclusive OR. So we don't normally tell you about exclusive OR in your first year programming courses. Excuse me. Exclusive OR is the same as OR unless both the values are true. So exclusive OR means one of the two values has to be true for the result. Exactly one of the two values is true for the result to be true. Right, so 0 XOR 0 is 0. 1 XOR 0 is 1. Right? 0 XOR 1 is 1. But 1 XOR 1 is 0. Right? So exactly one of the two values is 1. And so the caret operator is your XOR bitwise operator in C. So there's my number x, there's my number y. I take the exclusive OR of x and y. Anywhere where there's exactly 1, 1 in the two numbers, you'll get a 1 in the result. Right? So there's a 0 and a 1 here, so you get a 1 here. There's a 1 and a 1 here, so you get a 0. And there's a 0 and a 0 there, so you get a 0 there. Right? There's a little C code that reproduces that result right there. So if you run that, you get the exact same result here. Right? So again, if you analyze the result of XOR, if you have a bit x and you compute its XOR with 0, you get x. Right? And if you have, why did that become a vertical bar? Sorry. I don't know what happened there. Right. And if you have x and you take the exclusive OR with 1, that's the same as flipping the bit. Right? So it's the same as not x. Right? So if x is 1, the result is 0. Right? And x is 0, the result is 1. Right? Okay, so just like with and or, you can form a mask and then use XOR and apply the mask, and something will happen. Right, and so the useful thing you can do here, if your mask has a 0 in it, right, and you apply it to a number, then the bit in the other number won't change. Right? If your mask has a 1 somewhere in it and you apply it to the number, right, then the bit in the other number will flip. Right? So you can flip bit. Now you can selectively flip bits by applying a mask. Right? So here, my mask is all zeros and then a 1, so I'm going to always flip the least significant bit here by using XOR. Right? So when I compute the XOR of X and the mask, right, if that's a 0, the result is going to change to a 1. All the other bits will remain unchanged, right? Because X XOR 0 is equal to X, right? So all of these bits remain unchanged, right? Here, again, all of these bits in X will remain unchanged, so all of these will stay the same, right? But this bit will now flip, right? So XOR lets you selectively flip bits by using 1s in your mask. And now, instead of going from uppercase to lowercase, I can go from uppercase to lowercase or lowercase to uppercase. So I can toggle the case of a character now. It's going to be the exact same code as before, except now I'm going to use XOR instead of, where to go? Sorry. So here I took my character C and took the OR with 32. In the next example, I'm going to take C, right, and I'm going to take the exclusive OR with 32. So if I start out with an uppercase letter, it's going to flip to lowercase. If I start with a lowercase letter, it's going to flip to uppercase. Right, so there's my lowercase alphabet, and there's my uppercase alphabet. So I'm going to convert the uppercase to lowercase first. Right, so starting with that, you end up with that. Right, and then you can go the other way. So starting with the lowercase letters, you can flip them to uppercase just by computing the XOR with 32. And all that's happening here is I'm just flipping one bit in the character. So those are your four of your fundamental operations, bitwise operations, right? And you can see already, just using those simple operations, you can start to do some curious stuff. There's two more important operations that we need to talk about, though. And so those are the bit shifting operations. So if you're given a bunch of bits, or if you're given some value that's made up of a bunch of bits, you can shift the bits in those values, left or right. Right? So given an integer value, you can shift the bits, k positions, to the left or right. You have to be careful when you do this. So when you're shifting bits, you want to make sure that either the value that you're shifting the bits in is unsigned, or when you shift the bits, you have to be careful that your overflow isn't going to happen. Excuse me. All right, so there's two types of shifts. There's logical shifts and arithmetic shifts. So a logical shift simply takes the bits of the number and just assumes that they're zeros and ones. Right. An arithmetic shift looks at the bits of the numbers and treats the values as though they were belonging to an integer value. Right. And so there is a difference here. All right, shifting left. Is there a whiteboard? I don't have one. Does anybody have a whiteboard marker? Anybody? Okay. All right, so let me do this in... where did code get to? Okay, so imagine that we're working in base 10. So I'm going to write down a base 10 number using 4 digits. Right? So 0005. Right? So I'm always going to use 4 digits to write down my base 10 number. If I shift the 5 one position to the left, what do you get? You get 0050. Right? If I take the 5 and shift 2 positions to the left, what do you get? You get 0500. Right? And if I shift it 3 positions to the left, you get 5000. And so compared to the original number, right, shifting one position to the left, right, is like multiplying by 10. Right? So that's multiply. Right? So it multiplies 5 by 10 and you get 50. Right? If you shift two positions, right, not surprisingly, that's like multiplying by 10 times 10, or 100. Right? And if you shift three positions, that's exactly like multiplying by 10 times 10 times 10. Right? The same is true in binary. Right? If you shift a binary number one position to the left, the bits of a binary number one position to the left, it's like multiplying by 2. Right? You shift it two positions to the left, it's like multiplying by 2 squared or 4. Right? You shift three positions to the left, it's like multiplying by 8, 2 cubed. Right? And so when I originally wrote this notebook, I did it in a very rigorous way. So here's the mathematics for explaining all that. But I think it's much more intuitive if you just think about what happens in base 10. Right? Shifting digits in a base 10 number left is like multiplying by 10. Right? If you want to write it out mathematically, you can. So if you want to follow this, you can read through it and make sure that I typed in everything correctly. Right? But the end result of all of this is, if you have some binary number x, and you shift the bits k positions to the left, that's like multiplying the result by 2 to the k. Okay, so you have to be careful when you do this, though. So the question is what happens to the? Well, let's go back to code. Right. So when I shifted these digits to the digits to the left, right. So when I shift that to one position to the left, the question is what the heck happened to that first 0, right? And so the answer is it falls off the front of the number. Right. This sort of looks like it wraps around. That's not what's happening. It falls off the front. Right. If you shift two positions to the left, those two digits fall off the front of the number. Right. If you shift 4 positions to the right, right, you're going to get that. Right, which is not like multiplying by 10,000, right? You've shifted all the bits. You've shifted too many positions to the left, right? And the 5 fell off the front. Right. So in a logical left shift, that's exactly what happens. Right. So in a logical left shift here, this is a shift of two positions, right? That one shifts 2 positions to the left, so it just falls off the front of the number. Right? This one shifts 2 positions to the left, falls off the front of the number, right? And all of the other digits manage to stay in the 8 bits of the number. Right? Zeros get shifted in from the right. Right? So that's a logical left shift. Now you have to remember that you can apply these shifts to signed values. Right? So if you have an unsigned value, this is exactly what happens. If you have a signed value, remember that the first bit is in 2's complement is significant, right? If it's a 1, you know the number is negative. So in an arithmetic shift, the arithmetic shift tries to preserve the sign of the number, right? What exactly does C say it does? So it probably tells you somewhere here. So if you're using 2's complement for the in an arithmetic left shift, it behaves the same as a logical left shift, except when overflow happens. Right? And so when overflow occurs, the exact value of y, of the result, might depend on your compiler or your computer. Right? So your shift operator in C, the left shift operator, is less than. Right? So x is some value. Right? Less than, k is some unsigned integer number. Right? That's the number of bits in which to shift left. The standard says if you use a negative number for k, the result is undefined, so you can get any result. Right? Your program will probably compile, it will probably run. The result will depend on your compiler. If k is larger than the number of bits in your number, then the result is also undefined. Right? So if you have a 32-bit int and you shift by 33 places, the result is undefined. So for unsigned types, the left shifting behaves exactly the way you expect it to. Right? Your bits fall off the front of the number. Any overflow that results is will produce the value that you would expect given what left shifting, right? Given that you're multiplying by 2 every time. Now, the funny thing in C is that if you have a signed number, so if x is signed, and you shift by k bits, and the result overflows, C says the behavior is undefined, right? So if you start out with a negative, if you start out with a signed number and start to shift, right? Once overflow happens, there's no guarantee of what value you're going to get. So here's an example of shifting. So we're going to start out with this number here, 23, which is that, right? And we're going to shift by 1, 2, 3, and 4 positions, right? So let's see what we get when we run this. Okay, so start with 23, it looks like that, right? Shift 1 position, everything should move over 1 position to the left, right? And the first 0 should fall off the front of the number, right? And so you can see that is, in fact, the shifted version of 23. Right? Shift 2 positions to the left, so everything moves over 2 positions relative to the first line. Right? And you can see that is, in fact, the shifted version of x up there, of 23. Right? You shift 3 positions, the 1 is now at the front of the number. Right? And if you shift again, the 1 that was here falls off the front. Right? And so you get the 0, the 1, 1, 1. And then the 0, 0, 0, right? And that produces 112, right? Which turns out to be exactly the result you would get if you took 184, multiplied it by 2, and then wrapped it around so that it fit within an 8-bit value. And so that behaves exactly the way you'd expect it to work. Now, what happens if you have a negative value? So remember, in a negative value, that bit's always 1, right? And so when you do the left shift, that bit does not fall off the front. Right? The compiler is going to try to preserve the sign of the number. Right? So we're going to start out with, what do we start out with here? Negative 15. Okay. Here. Run that. Okay, so we start out with negative 15. Right? Because x is a signed value, the compiler is going to do an arithmetic shift rather than a logical shift. So in an arithmetic shift, we're going to try to preserve that bit there, right? Which we do. So there's the 1 there. Right? These bits will move over 1 position to the left. Right? That bit there will fall off the front of the number. Right? So we're going to end up with those numbers there, those digits there, sorry, in these positions here. Right? And we end up with the value minus 30, which is minus 15 times 2. Right? If you shift this number 2 positions to the left, right, the first 2 1s will fall off the front, the ones that are highlighted will fall off the front of the number. Right? The sign bit will be preserved, and these bits will move over 2 positions to the left, right? Which is what we get there. Right? And we get minus 60. Right? You do it again, you get that result there, which is minus 120. Right? Now, if you shift again, this is where the overflow occurs. Right? And so now, when you shift again, the 1 now falls off the front. Right? Because 120 times 2 is 240, minus 240, which does not fit in the range of an 8-bit signed int. And now you get that result there. Right? So that bit this does in fact shift 1 position to the left, like that. Right? But now the sign bit has also fallen off the front. Right? This step here, or the result here, you cannot rely on that being the result. Right? This happens to be the result on my computer. It's probably the result on most of your computers. You might be able to find some computer somewhere with some operating system where this isn't true. Right? So arithmetic left shift, compiler tries to preserve the sign of the number. Right? Logical left shift, so with an unsigned value, the bits just fall off the front. Shifting right is exactly the same thing, except the bits go to the right. So again, starting with, I guess I'll start with a larger number this time, 5, 6, 7, 8. Right? If I want to shift this 1 position to the right, right? All the digits move 1 position to the right. A 0 comes in from the front. Right? The 8 falls off the end, so you get 567. Right? If you start with the original number, shift 2 positions to the right, you get 2 zeros in at the front, then the 5 and the 6, the 7 and the 8 fall off the end. right? And then 0, 0, 5, and then 0, 0, 0, 0, like that, right? And so if I start out with that, this step here, so shift 1 position to the right is like dividing by 10. So if I take 5, 6, 7, 8 divided by 10, you get 567.8. So divide by 10, then truncate. Right, so throw away everything after the decimal point. Right. Shifting 2 positions to the right is like dividing by 100 and then truncating. Right, and similarly, shifting 3 positions to the right is like dividing by 10,000. Shifting 4 positions to the right is like dividing by 10,000. Right. And so the exact same thing is true in binary. Right. If you shift a binary value 1 position to the right, it's like dividing the value by 2 and truncating. Right. If you shift 2 positions, it's like dividing by 2 squared. If you shift 3 positions to the right, it's like dividing by 2 to the power 3. Right. And again, the math is all here if you want to check my math. So there's the result, right? So your result, if you take x, shift the result k positions to the right, it's like dividing by 2 to the k, and then taking the floor. Right? So that's the floor operation. Okay, so there's a logical right shift. So again, there's a logical and arithmetic right shift. Right? So for the logical left shift, the bits on the right simply fall off the end of the number, right? And zeros get shifted in at the front of the number. Right, so shift 2 positions to the right, you get two zeros in the front, right? This one moves 2 positions to the right, that one moves 2 positions to the right. This 0 moves 2 positions to the right, but the 1 and the 1, they fall off the end of the number. Again, in an arithmetic right shift, if you start out with a negative number, the compiler tries to preserve the sign of the result, right? So if there's a 1 sitting in the front and it's an arithmetic shift, right, the compiler will repeat the digit instead of shifting in zeros. Where's the 1? Here it is. Right. So in an arithmetic right shift, this is of 2 bits to the right. Right. These bits fall off the end. Right. Instead of the 1 shifting over 2 positions to the right, though, it also gets duplicated into the front 2 bits. Right. So the sign bit gets shifted and duplicated. If your sign bit is a 0, the same thing happens. But if the sign bit's a 0, that's basically like shifting an unsigned number, right? Because the numbers, the value's positive anyway. So the right shift operator in C is just the double greater than operator, double greater than symbol. Right? So x greater than k shifts the value of x k positions to the right. Again, k has to be 0 or positive. And should be less than the number of bits in the value x. All right, so for unsigned types, a right shift always works, right? Stuff just falls off the right-hand side of the number. The C standard says if you have a signed value and it's negative, the result is implementation dependent. Right? So in other words, it depends on your compiler and operating system. Right? If your value of x is a signed value and it's positive, then everything works the way you want it to, right? It's the same as a logical shift. Okay, so right shifting a number. This is right shifting a unsigned number. We're going to start with 23, right? So shift 1 position to the right. It's like dividing by 2. So 23 divided by 2 is 11. Throw away everything after the decimal point. Is 11.5. Throw away the 0.5. You get 11. Right. 11 divided by 2 is 5.5. Throw away the 0.5, right? And so on and so on and so forth. Right. If you shift a signed value, starting with minus 15, right? So minus 15, did I say it's truncate? It's not truncate, it's floor. So minus 15 divided by 2 is minus 7.5. The floor rounds towards negative infinity, so you get negative 8. It's not negative 7. I said truncate, it's not truncate. It is the floor, right? Minus 8 divided by 2 is minus 4. Minus 4 divided by 2 is minus 2. Minus 2 divided by 2 is minus 1, right? And so here we actually get the correct results. All right, so those are your 6 basic operations, right? You have not, and, or, exclusive or, and the 2 shift operations, shift left and shift right. All right, I'm going to call it quits there. The next lecture, I'm going to show you what you can use these operations for, and we're going to work with some color values. So I'm going to show you how color values are often encoded in many computer graphics applications, and how you can use the bit shift operators and the bitwise operators to extract the individual color components. Don't forget, you have a midterm on Thursday, sorry.